My friend, I have a killer exam problem for you, and stick with it. Go through this with me. And if you do, you'll understand a lot of concepts that have to do with Gibbs free energy and the equilibrium constant. So let's jump into it. So for a saturated brine solution, the concentration of NaCl equals 359 grams per liter. And the question is asking us to determine the change in Gibbs free energy, or the reaction Gibbs free energy, for the dissolution of NaCl. So it doesn't look like we have a lot of information, and we're given a molar mass, but we want to know what the reaction Gibbs free energy is. So how do we proceed? Well, we want to know something about the dissolution. So that means that's breaking this up into a solution. So to do that, we'll write it out as NaCl, because that's what we have. Now for dissolution, it's when it dissolves into Na plus into the respective ions. So Na plus aqueous, because it's being dissolved, plus Cl negative aqueous because it's being dissolved. Okay, now this says this is a saturated brine solution. So that means we've dissolved as much as we can, but we could dissolve more, but the solution won't allow us to. So we still have some solid in there. So this is an equilibrium reaction that we have going on. So if we think of it, what's going on? We have this container and we have a bunch of salt at the bottom. I know the salt is white, but the background's white, so I'll just make the salt red. And this is like the solid down here. Actually, I'll just make it like a clump. And then we also have the NaCl dissolved in here. Now, there are two different ions, so you can think of like one ion for sodium plus, one ion for chlorine, but it's going back and forth. There's like this two-way equilibrium constant, or equilibrium going on between the solid and the solution here. And we want to know what the reaction Gibbs free energy for this is. So to do that, we want to know how far along this reaction the equilibrium lies. So like the equilibrium constant, I'll change it to blue. The equilibrium constant K is going to be equal to products over reactants. And it's the activities of the products, which in this case will be these. We'll say there's concentrations. This is a first year chemistry class, or a AP chemistry class. It's not like a second year or anything. So we're just going to say that these are concentrations. Really, they're activities over 1, because we don't include pure solids or pure liquids and solids in our equilibrium constant here. Now, so this number here, this concentration, this can tell us the concentration of how much of this can dissolve, which can give us the concentrations of these ions when it's in equilibrium, when it's fully dissolved, because this is how much dissolved. Okay, to give ourselves more room, we're going to start off with this 359 grams of NaCl for every 1 mole of the solution. And we want to find out how many moles of each of these ions there are. So we want to cancel out grams of NaCl, which is 58.99. Just want to double check here on Google. 58.44, very close. Okay, so 58.44. I'm multiplying this by a fraction here. 1 mole of NaCl. It's supposed to be a mole there. So if we do this, we cancel out grams of NaCl. So now we're in moles of NaCl, and probably don't even have to do this, but we know that for every 1 mole of Na plus that's produced, we have to dissolve 1 mole of NaCl, because it breaks up in a 1-to-1 ratio. So that's cool. And that gives us, I'll throw that into our calculator, 359 divided by 58.44, 6.143. So 6.143 moles of Na plus for every 1 liter of the solution. So this is our concentration. So we're going to get our equilibrium constant. So our concentration of Na plus is 6.143. We have sig figs, 3 sig figs. Molarity, moles per liter of NaCl. And then we can do the same thing. It's going to be the exact same number for Cl minus. If you don't believe me, we're going to set up the same situation here, and that'll give us moles of NaCl. But at this point, here we would multiply this by 1 mole of Cl minus for every 1 mole of NaCl. So it's still a 1-to-1 ratio. So it's going to be the exact same concentration, which is good because for every time this dissolves, we get 1 mole of this and 1 mole of this. So it always has to be a 1-to-1 ratio. Okay, so our equilibrium constant is now going to be the concentration of Na+. Technically, the activity, it should be unitless, but we're going to just put in molarities, and that will be fine for us, is 6.146 squared is, and remember the equilibrium constant is unitless. Oh, you know what? I can just do squared to this? I can just take the number I had and squared it. Okay, and that looks like it's squared. 6 squared is 36, so a little bit higher. So 37.737. 37.737. Okay, so that's our equilibrium constant. And we don't want the equilibrium constant. We want the reaction Gibbs energy. So we're going to use our equation here. The Van't Hoff, this is called the Van't Hoff isotherm. If you want to impress somebody at a party, then we'll plug it into here. Now, the R that we use, we want the R, if you look on your formula sheet, the one that has joules, so joules per mole Kelvin. Technically, Gibbs Free Energy is usually reported in kilojoules, but you probably don't have R in kilojoules. It's probably given to you in joules. Oh, what's our temperature? We need a temperature. Okay, so this comes up sometimes too. So see this little superscript? So this is under standard state, and this is a standard state of 1 bar, but it could technically be any temperature. It could be any temperature. But if it doesn't say so, then by default, we're going to assume it's 25 degrees Celsius. It's 298 K, but it doesn't have to be 298 K. Kelvin. If it doesn't give you a temperature, just assume it's 298 Kelvin. But at standard state, it really just means 1 bar. It could be any temperature we want. Okay, so we'll plug this in. Ln of 37.737 negative 8.314, 5 times 298 times, and the ln I think is way down here, of 37.737. It's a high equilibrium constant, which means the products are favored. So dissolving the sodium chloride is favored, is spontaneous, I should say. Negative 8958, so negative 8958. And our units are joules per mole because Kelvin cancels out. So joules per mole, or if we put in kilojoules, negative 8.96 kilojoules per mole. All right, so delta G is negative, which means the dissolving of salt is a spontaneous process at room temperature and at 25 degrees Celsius and at 1 bar. Okay, I hope you enjoyed it. Good luck on your midterms. Good luck on your final exams. Good luck on your quizzes and assignments. Let me know in the comments if you have any questions on any of your work material. And thanks for watching. All right, see you in the next video. Cheers.